So here's the heuristic. So let's say we have a CW decomposition of our manifold X. So you have some simplices like these. This is the barycenter, and you glue them along their faces. So I'll tell you how to construct a function that has the property that every K cell corresponds to critical point of index K. And so now your usual definition of Euler characteristic as the alternating sum of the count of K cells recovers this claim. Okay, so how's my function going to be? What it's going to do is on the interior of the simplex, it's just going to keep decreasing. And on the complement of it, it's going to sort of increase. I used a different color. Sorry about that. But yeah, green is supposed to be decreasing. And so you decrease along these directions and increase along the other adjoining directions. And you can write down local models for these functions. And the fact that these simplices glue together is what allows you to glue the function from each simplex to get a function on your whole manifold. And you can verify that this is C2. There are no other critical points. And this is how you prove the claim. So, of course, in this claim, one thing that's hidden behind, one thing that I'm hiding under the rug is that this side does not depend on the function f. And so one way of proving it, of course, is saying that this is equal to that. And so that does not depend on the function. And so invariant. And I'll leave it at that for the moment. And we'll come back to, getting genuine intrinsic proofs of invariance under the Morse function a little while later. Okay. But this just recovers a numerical invariant. What if we wanted something finer? What if we wanted, say, homology, singular homology, for instance? So let me outline how to get that. So this is a little confusing.
Sorry. Each cell is the directions in which.
Yeah. So Shubhaja asked this question about how is the K cell corresponding to a critical point of index K. So when you have your K cell over here, you move along in all the directions inside the cell, and those are the places where your function decreases. So it looks like a plateau of sorts. If this is your flattened picture of the
thing, you define the K cell from this Morse function.
No, you start with a CW decomposition and you're trying to come up with a Morse function on it. Yes. So yeah, this is a heuristic. This is not a proof, but it's supposed to sort of motivate what comes next.
Just to clarify, so the increasing directions are basically this K cell will sit inside maybe a K+1 cell, and so the other or normal directions are where it
yes, exactly. Yeah. Yep. So I'll come to that a little bit more. But what I wanted to, I guess, impress upon you guys was that a K cell, you should think of it as a critical point of index K. And now we're going to sort of reverse the analogy to build up what our homology ought to be. Okay. So. Yes. Homology. So guided by this intuition, what we try talking about the so-called stable and unstable manifolds. So let me define them. So the unstable manifold, the point P, is a set of all points Q belonging to X such that there exists path gamma from -infinity to 0 to X. Gamma is C1 such that gamma prime T is equal to negative gradient T and limit T tending to negative infinity of comma T is equal to P, your critical point, and comma 0 is equal to Q. So these are trajectories of this sort. You have a red critical point over here, and your trajectory. Okay, I should be careful about my color scheme. Okay, let's say green. Then it hits over there. It's supposed to be P. Okay. So keeping in line with that heuristic, this is supposed to be your K cell of sorts. And to put this on a firmer footing, it's called the unstable manifold. We can also talk about what the stable manifold is, which is counterpart to the other case, which is supposed to be. We first again give a picture of sorts. P, then so again Q belonging to X is that there exists some trajectory, this time from 0 to infinity. X is that this is 1 such that it satisfies the same differential equation. With limit T tending to plus infinity, T is equal to P and comma 0 is equal to Q. For the stable manifold. And this is supposed to correspond to your orthogonal directions to your K cell. Okay. So I've been calling them K cells, but let me. So let me back that up with a claim which I'll not prove. So I'll call it a fact. These are always homeomorphic to open disks. Well, by always, I mean in a generic situation. So when your Morse function is generic enough, when your metric is generic enough. So everywhere, whenever I make a claim, it's to be assumed that I've made a generic choice of metric and function. Yeah. Is this and the dimension of the unstable manifold is the index of critical point. Yeah. And dimension of stable manifold is n minus the index, which is where n is the dimension of your underlying manifold. Okay. All right. So I've backed up my heuristic about that being about a critical point corresponding to a K cell by talking about the unstable manifold being this, having the right dimension and it being a disk. Now I need to tell you what the attaching maps are, right? So instead of telling you what the attaching maps are, I'll instead directly tell you what the chain complex is that computes singular homology. Yeah. So this is a good spot for me to stop for questions. So are there any questions up to this stage? F is my Morse function on my Riemannian manifold. Oh, you start with the f. You start with the f to build this complex, and at the end, it turns out that the homology that this complex computes is independent of your function f. Yeah, yeah. So you fixed a function f on your compact Riemannian manifold.
Just a suggestion to draw the torus and the height for people seeing this plus sign.
Yeah. Okay.
A classic picture.
Yeah. Yeah. Fair enough. I was going to draw it a little while later, but now is as good a time. So, okay. So here's a torus and your function f is. This is your function f, which is a height function. And so it's, yeah. This is, I always forget which color I've used for which.
Green for down.
Green for down, okay. All right, so yeah, the red points are your critical points, and here are the directions where things are going down. One there and one back. Then here are the directions. So going up. And everything is going up over here. So the indices of these critical points is going to be +2, it's going to be 1, it's going to be 1, and there's going to be index 0. As we shall see in a bit, this is not the best Morse function on the torus that we can have. And instead of trying to change this, I'll try drawing another figure that you should keep in mind for that is going to satisfy the genericity hypothesis that I mentioned. So here's that figure. This is just a wobbly sphere. So you just taken a blue sphere and sort of deformed this bit over here to get it into the shape. And again, your function f is still a height function. And so that's here are your critical points, and it's increasing.
There's an undo button as well.
Oh, okay. Okay, that's good to know. Yeah. Here and yeah. So again, your indices are +2, 1, then 0. Okay. All right. So with this. So now, okay. So how do I? So my chain complex that I'm going to form is it's going to be the free abelian group generated by critical points with index equals k. So let me use the following notation. So the superscript is supposed to denote the index, and I is just some indexing variable. Okay. So this is the chain complex that I want to define, and I need to tell you what the differential is. So and this I'm going to define as follows. So we call our So our unstable manifold, this is diffeomorphic to an open ball of dimension index of P, right? So in this, you can talk about, so I'm going to define U prime of P as the disk of radius half sitting inside this. Okay. And so why I'm using this weird definition will become clear in a moment. Okay. So I'm going to now define some numbers, which are just going to be if yeah. You take let's see, signed count of the boundary of U prime of corresponding to K I, then intersect this with stable manifold corresponding to K minus 1 J. So the figure that I use to illustrate this is as follows. So over here, so color. Yeah, so over here, if I wanted to compute the differential between to compute this number for these two critical points, then I'll count basically look at this stable, this manifold, take a boundary of it. So look at that segment there, and then look at the unstable manifold corresponding to this. So that's going to be all of this. And so you can see that both of these intersect at one point. And so in this case, that count would be equal to 1. Yep. And so how we'll define our differential is as follows. It's just going to be EKI is equal to summation over J of Cij Ek minus 1 times J. This is going to be our main formula. And this is a good example to sort of try computing it for, and I would encourage you to compute what the homology is in this case and see that it recovers the homology of your two sphere.
So the left, that's EKI, right?
Yes, thanks. ZKI and use homology.
So this doesn't quite work for the torus, I think.
Yes, which is why I like to avoid that picture. It is great for showing what a Morse function is, but it's bad at talking about this trajectory. And so just to expand on Shubhajoy's comment, what Shubhajoy's point is that when you have critical points, you need to look for these, when you have two critical points which differ by index 1, then you should look for the intersection of their unstable and stable manifolds. And this sort of works if you keep the indices different. But here there's an issue where you have two critical points of the same index and their stable and unstable manifolds do intersect. This is going to be a problem later, but I'll recast it in a slightly different manner. So it might be slightly difficult to see, but I'll expand on it.
You have to distort the torus a little.
Yeah, you need to distort the torus, but it's getting a little ahead of ourselves. So I just wanted to expand on Shubhajoy's comment that this torus is not the best picture to keep in mind. This picture is better. So in particular, I guess, just to add one last thing, if you try computing this complex for this torus, you'll see that d squared is not equal to 0. And that's the main issue. Whereas for this one, it'll turn out that d squared is equal to 0. This is a little confusing. Okay, so the claim that I want to make is that first t squared is equal to 0 and kernel dk mod image dk is isomorphic to the kth singular homology of X with integer coefficients. So to prove this claim in earnest, you need to first, so when I mentioned over here that you take count of intersection points, you need to actually take an oriented count of the intersection points. And so that goes into talking about, explaining how these manifolds are oriented and so forth. So I'll not go through the whole of it, but I'll give you again a sketch. And I'll say a good reference is Nicolescu's Invitation to Morse Theory book. So, all right, let's go on with the sketch. So most of this rests on the following key observation. So is that X admits a CW decomposition with K cells being the unstable manifolds with index of P equals K. These are going to be your K cells. And the attaching map is sort of described by how the stable manifold and the unstable manifold intersect each other. And this number that you see over here is a manifestation of that. But of course, this requires more because you need to say that they glue on in a continuous fashion and whatnot, whereas over here, you're just counting some intersection points. But once you have this key observation, then the final thing that's much simpler to see is that the attaching maps define TK via cellular homology. And you can directly check that the definition that I gave agrees with what you get from cellular homology. And since cellular homology computes singular homology, you have just showed that both that d squared is equal to 0 and that the homology of your chain complex is the singular homology of your CW complex. Any questions at this stage? So what time is it? Okay, all right. Okay, yeah, all right, we're doing fine on time. Okay, if there are no questions, I'll keep moving forward. So even with this very sketchy picture that I've shown you of what Morse homology is supposed to be in this finite dimensional case, there are quite a few things lacking. Well, one of them being I've not given you proofs, but even beyond that. So here are some shortcomings, and why I call these shortcomings is that these really restrict you to finite dimensions and don't allow you to directly jump off into infinite dimensions. So what I'm going to spend the rest of the lecture is going to be reformulating what I just said, but in a more clever manner so that a lot of it just goes verbatim to infinite dimensions. Okay, and this is how we'll end up constructing Floer theory in the very end. Okay, so with this in mind, let me first tell you what the shortcomings are and tell you how we can overcome them. So the first chief difficulty is analytic. And so what this means for us is showing that UP SP. So this unstable and unstable manifolds are disks, and other things about how they intersect transversely, and how you can make sense of the counts of points that I was talking about. I mean, the main issue here is that you're dealing with an ODE over here. So your usual theorem of ODE tells you that once you know what point you're starting at, you can uniquely solve your ODE. But this is just not true in infinite dimensions. If you look at the analog, which is going to be some equation of this sort, so you're going to look at something like DTF plus say Laplacian F is equal to 0. This is a parabolic PDE and generally not that well behaved. And so this is something that, I mean, this particular one might be well behaved actually, but the point that I want to get across is that you don't want to put yourself in a situation where you need to, at every stage, you need to deal with a PDE that's just hard to analyze. So this is one way of difficulty. And the other difficulty is about satisfying genericity. What do I really mean by this? What I mean is it's cumbersome to formulate and prove things like this is P intersect S of Q, that these things are well defined and things of that sort. So for example, for the torus, you'll see that this is exactly the reason that causes issues with showing that t squared equals 0. Okay. This is one, and we also want, so let me put this straight thing. So the proof that I gave was not intrinsic. What it depended on was saying that, okay, you can build a CW decomposition, and from there you notice that your D is the cellular differential, and from there it follows that t squared equals 0. But in infinite dimensions, you simply don't have the luxury of showing that whatever space you're looking at, that this thing is going to define the CW complex. In fact, for a variety of reasons, that's just a bad idea to try doing it that way. So what we would like is an intrinsic proof. So this is not to say that we don't have one in this setup, but at least I've not found a simple one that easily generalizes to infinite dimensions. So the one that I'll talk about later on, it'll be clear that this just relies on a particular qualitative property of some moduli space that we'll be constructing. So what we would like to do is overcome all these three, and it turns out that there is a good way to do this. And I think Nicolescu's book calls this Morse-Floer homology to distinguish it from just your vanilla Morse homology. And that's what I'll be talking about. So at this stage, if you had any questions about just the singular Morse chain complex and all of that, this is a good place to ask because we are going to be soon leaving that realm. Oh, the second point, right. So, okay. Okay, the relevant fact over here is that, okay, this is, okay. So here's the relevant observation. observation slash fact, I guess. So generically, the dimension of Q prime P intersect S of Q. This is supposed to be index of P minus index of Q minus 1. So in particular, if this were negative, then this intersection is supposed to be empty. And this will fail. Like in the torus example case, you have two critical points of index 1. So this whole figure is going to be -1. And for that, you'll still have some points of intersection. And that's bad because it'll show up later on. I mean, in one case, in one sense that it manifests itself is disproving that d squared equals 0. So what you need to do is you need to perturb your function and Riemannian metric so that this does happen. And that's it. This first of all will rely on showing that U and S are disks and then analyzing how these manifolds intersect each other. So that's sort of like what I wanted to allude to in the second point, which is that showing things like this is cumbersome, partly because it relies on the analytic difficulty from the first point. Okay. So let's words. Okay. So to try reformulating, we'll focus on just the things that we need. So what we would like is a reformulation of what the coefficient Cij that I mentioned a little while back were. Okay. So let's try thinking about what the intersection of your stable and unstable manifolds correspond to, and that will lead us towards a reformulation. Okay. So let U be some point inside intersection of unstable manifold of P minus and the stable manifold of P plus. So first of all, these will intersect in, there'll be infinitely many points. I'm just saying pick one of them. This is not the count of intersection points that we're looking for. But what this tells us is that there exists two trajectories, one gamma minus from x and another that's gamma plus from 0 to infinity x with the following properties. So both of this meet at the point U, and both of these trajectories satisfy this equation. And finally, we also have the right limiting values. Okay.
So here, minus and because differ by one in index differ by one.
You don't even need to assume that, but that is the context we'll be concerned with. But at the moment, you don't even need to worry about that. Yeah. So notice that at no point did I say that U was isolated or anything of that sort. In the earlier one, I agree that those counts make sense only if you have a discrete set of points. Okay.
So gamma is the same as nu?
Yes, that's just my bad handwriting. I think, yeah, both are supposed to be gamma. So yeah, I guess I've not gotten used to this board enough. All right, so with this, what we'd like to now say is that, okay, now you can join both of these trajectories, gamma minus and gamma plus, to get gradient trajectory. So, and that's not a big deal because the point is that both, sorry, at u. So both of our derivatives both of our trajectories, their derivatives at zero coincide, and they're just the gradient of f at this point u. So that means that we can get gamma mapping from R to X, and gamma is now C1, such that gamma T equals gamma minus T if T is less than 0, and gamma plus T if T is greater than 0. And this now has the property that limit t tending to plus or minus infinity, gamma t is equal to p plus or minus, and gamma 0 is equal to u. Okay, so this is great. This means that we can define a moduli space between p minus and p plus as gamma, which is maps from R to X, gamma C1, with the property that limit tending to plus or minus infinity, gamma t is equal to p plus minus, and it satisfies the gradient flow equation. And above it just follows because gamma plus and gamma minus both satisfy this gradient equation. And so this whole trajectory satisfies it as well. And we now have sort of an evaluation map sorts, which goes from p minus p plus to unstable manifold plus stable manifold plus. And this is just you take gamma, then map this to gamma of 0. And this is a bijection. Okay, right now we still don't have a topology on this moduli space of trajectories, but we'll get to that shortly. Any questions at this stage?
Yeah, I have a question. Is this, can you hear me?
Yep, I can hear you.
Okay, yeah. So is when you say this is a bijection, do you mean that this is up to reparametrization of the trajectories?
I have not reparameterized my trajectories. In fact, if I did, then I could not talk about evaluation at 0.
Ah, I see. Yeah. Okay, great. Thanks.
Yep. So these are actually all the points of your intersection of unstable and stable manifolds. But okay, that leads me to the next thing about reparametrization, which is, recall that what we cared about was the intersection of boundary of u prime, which is like a half disk sitting inside the full one disk, with the stable manifold. So to get that, what we'll do is, as I think Balarka pointed out, that this is going to be actually the count of reparameterized, like yeah, parameterized that. Never mind. I'll say this out a little while. Okay. So, notice that this space as an R action, which is a real number S acts on gamma, and this gives a new trajectory. So this new trajectory evaluated at T is just gamma of T plus S. Okay. So, so the first thing to notice is that whenever P plus and P minus are not equal, this R action is free. And that's just because your trajectory is not constant anywhere. Yeah. So that's great. What that tells us is that this is a sensible reformulation. We talk about unparameterized trajectories, which is just going to be plus modulo the TR action. And so now this is going to be, okay, let me just jump straight to the claim. So the claim is that when the index of P minus is equal to index of P plus 1, then the Cij trajectory and the Cij count that we were talking about, this is actually just a count of this space. And the only point to notice beyond what I've already said is that this reparameterization by R is what allows you to go from U to the boundary of U. Going to the boundary is sort of essentially fixing a choice of distinguished choice of what the origin should map to under the path. And so that's why we needed to reparameterize. But this is great. Now, after this modding out by these reparameterizations, what I've got is I've got something that now no longer has anything to do with the unstable or stable manifolds. So I've dealt with point 1. If you're trying to go and do this in infinite dimensions, you now only need to count these trajectory spaces, because that's still easier said than done, but that's an improvement. Any questions at this stage?
Yes, so did you assume some genericity for this Cij or we are just?
To define Cij for your differential, you need to assume genericity, but I guess what I wanted to say was that independent of genericity or whatever, just the definition itself, this makes sense on the rows.
That cardinality will be infinite often, right?
Yes, yes. So what I guess I had in mind was that this intersect S of Q is in bijection with, I'm just going to use this symbol, but your moduli spaces don't have a topology yet, but this is in bijection with this. That is what I really wanted to clear. Yeah.
That is always true.
Yes. So if one of them is discrete and finite, so is the other. All right, so this is good that we have got rid of the unstable and stable manifolds, but now the problem comes to how do you even define M? I mean, you can define it as the space of trajectories, but if that is the only way you're going to talk about it, then you're not done much. You still have the issue of trying to describe what this is in some other context of infinite dimensions. You still need to solve some parabolic PDE, which is a problem. So here's how we're going to sort of reformulate it, and really this will this will really show itself that this is a better formulation when we actually get to the technical details of Floer theory, which will be done later. But to set the stage, let me just.
So this uniqueness of ODE that you mentioned earlier, that's just to show that this is a bijection.
Yes, indeed. Yes, indeed, exactly. Yeah. So we've sort of pushed that into how we're defining M itself. And so, yeah, so I've still not gotten rid of the ODE thing. Still need to do something to get rid of that. And so what we're going to do is we're going to try describing our moduli space M before this M check thing. We're trying to define it as the zero set of some in some equation of sorts. And the hope is that this equation will have nicer properties and somehow you can, say that, okay, the zero set of this equation is well defined and you can actually compute it and stuff. Okay, so to this end, let me talk about describing M as a zero set. Okay. All right, so for a moment, let's fix critical points. So over here, I'm assuming nothing about the indices or anything. We're just going to keep going and tell what that is, because the one part of this reformulation is we want better proofs of what this genericity and all of those mean. So we're going to work under the assumption that nothing works in our favor. And then we'll see how to fix things.
Sorry, Deeparaj, technical point, you accidentally zoomed in, can you?
Oh,
Become weird.
is this better?
Pull it down a little and just make, can you just pull down the screen a bit temporarily? Pull down so that we can see. No, the other way around.
Oh, okay, sorry.
Zoom it so it's the previous size. The way the final print will look weird.
Yeah, I think,
Yeah, sure.
yeah.
Now it's fine.
Okay. I mean, I have a set of notes. I think those will be better
Yeah, sure.
set because, yeah, I've still not gotten used to writing this directly
Yeah,
and,
sure.
yeah. Okay, so let's pick some critical points. Now we can define a space of paths from P minus to P plus, which is just going to be R to X, where comma is C1 and we have limit tending to plus or minus infinity. So this is just a space of paths that limit to the critical points on either end. And our moduli space is now going to be a subset of this. So when I say a subset, and in fact, I've said it's a zero set, I need to now talk about a function on it. Was there any?
Sorry, so this part has nothing to do with your ODE. You just took all parts.
Yeah, I just took all paths. These don't satisfy anything. Yeah. Right, let me just talk about this. So we're going to define a vector space for every path in this path, for every point in this path space. So given a fixed path, which is C1 and which has this, we're going to define some vector space over it. And here's what this vector space is going to be. So this is supposed to be sort of like sections of this vector bundle vanishing at infinity. So let me write that out in detail what this is. So this is just psi, which has the following property. Psi is some function from R to another space, and it has the following property that psi t is supposed to live inside the tangent space of X at gamma t with the property that psi t as limit t goes to plus or minus infinity is supposed to be equal to 0. So what you should keep in mind is following. So you have your path. These are your critical points, P minus, P plus, and your xi element is sort of supposed to be okay. You push stuff off a little bit here and there. You can even move along the path, do whatever. Just the fact that when you get close to either of these points, you're supposed to vanish. So this is not supposed to be there. So what you should intuitively think of this is the sort of tangent space of at the point gamma. So you can instead think of this as tangent space of the path space. Okay. So what this gives us is a vector bundle. So I'm just going to call it E instead of calling it that, just for clarity reasons. Where pi inverse of gamma is just supposed to be E gamma. So these are vector bundle. And what we're going to look for is a section of this vector bundle, and the zero set of this section is what is going to define our moduli space. So is the definition of the vector bundle clear? Okay, cool. Okay, so here's our section. So for every path gamma, I'm supposed to tell you a function xi that has those properties. So here's how I define it. It's going to be r prime t plus so notice that both components lie in the tangent space of X lying over gamma t. This is just because it's the derivative, and this is also basically by definition. So now this defines a section of E over P. By that, all that I mean is that anyway, so this defines the section, and our moduli space by definition is the zero set of F. So this is just the intersection of this section with the zero set, and this is going to be our moduli space. So what we have done with this is that we have now pushed all the brunt of showing that this is, of the right dimension. Generically, it's empty. Generically, it's transversely cut out and all of that, into just showing that this function F is transverse and has the required properties. And we'll see that later on in action, this actually does get us through. And so to the point that Ved made earlier, that we're still not got rid of our theorem of ODE. Now I've twisted on to what F does. And so now instead of appealing to the theory of ODE, we are just going to get our hands dirty and show that F has the required properties. Okay. Now some of you might still complain that, okay, this looks great and all, but this still looks like a parabolic PDE, right? I'm not changed that yet. And that we'll get to see only when we get to the actual equations, how there's a neat little trick that somehow incorporates somehow sort of, you have more symmetries than what you'd expect, and modding out by these more symmetries, your parabolic PD becomes essentially elliptic. But anyway, if that comment didn't make much sense at the moment, hopefully it makes more sense when we get to the actual details.
Question, you mean the R plus symmetry is what you're meaning? I mean,
No, that's not it. Yeah, this is, I don't know of a simple analog in finite dimensions. Yeah. So I just want to point out that okay, I've already said that. Never mind.
Yeah, at this stage, it just looks like you're nothing has been done.
Right. So this is
Curious to see how exactly this will accomplish
the goals, right?
Yeah.
Right. So I think the only thing that I'll explain to a reasonable degree is an intrinsic proof of D squared for today. And the actual implementation of this framework, that is where you'll see that this framework is what really gets the job done. So you're right to complain that all of this is just, swirling around words and like coming up with like new sentences out of the old one, and you're not adding anything. But it's important to have it in this framework because this framework goes over verbatim, whereas the earlier one does not. Okay, but one upshot that I do want to mention is that we've got a topology on this moduli space now, because your space of paths has a topology on it. So not just a topology, I've given them a C1 manifold structure as well. Okay.
These are Banach manifolds, right?
Yes, I mean, I've not been very careful with the formulation, but we'll work with the case of Banach manifolds. Yeah.
Modeled up some Banach space.
Yeah. So we'll be working with Sobolev spaces rather than CK spaces or smooth functions or anything of that sort. So yeah. And I guess since we talked about that, the key point is going to be that your F is going to be Fredholm in the most general case. And so that is what allows you to sort of get a hold on things. And I guess the key contrast is that parabolic PDs, their linearizations are not Fredholm, but somehow this F turns out to be Fredholm nonetheless.
So in this case, they're actually finite dimension. The finite.
No, even in the finite Morse theory case, all of these path spaces and such are infinite dimensional.
But moduli spaces themselves are finite.
Yes, indeed. Okay. So the remaining time I'll sketch how we can get an intrinsic proof of D squared equals 0 in this formalism. And okay. So let's.
Sorry, before, just to clarify.
Okay.
In this formalism, even the torus non-example fits this formalism.
Yes, we're not assumed anything about genericity or anything of that sort.
So, but then your D will correctly count, etc. or something.
No, I'll talk about how the compactness. So in this case, what we'll do is we'll say that D squared actually counts the boundary of some moduli space.
Okay.
And to get that the boundary is in fact a manifold of the right dimension and whatnot is where all of the transversality and all of that gets in. Yeah. So to start off, let's compute what d squared is. And so this is a sum over L, let's say. So d squared is going to be a matrix and the matrix entries are given as follows. You sum over all critical points L that lie between, sort of like EI and EJ, and you look at all these moduli spaces and sum them up. So I've already mentioned over here in the notation that these points are going to have index lying exactly between K and K minus 2. So, okay. So what are these trajectories looking like? We have critical points of this sort. You have trajectories that go along like this. I'm using the wrong color scheme. Give me a sec. Okay. So these are the sort of things that we're counting. Places where you can concatenate two paths together. Okay. So now the observation is that there is a path that's lying pretty close to this sort of broken trajectory. Where by broken trajectory, all I mean is just a union of a bunch of trajectories that all line up. And so now here there's a blue trajectory that goes directly from EKJ to EK minus 2, EKI to EK minus 2J, which is pretty close to this broken thing. So what this suggests is that sorry. Where index of P minus is index of P0 plus 1. Is it minus 1? I think it's minus 1. So what this suggests is that this product of these moduli spaces in this context at least should lie inside some sort of compactification of moduli space from P minus to P plus. Because notice that if we keep taking this blue curve closer and closer, like this, then in some sense it converges to this broken trajectory. But this broken trajectory itself is not in the space of trajectories. So that tells us that, okay, this moduli space, even after. So notice that this moduli space is of without the plus sign, which is supposed to denote the compactification. It's manifold of dimension plus 1. Yeah. So what this it needing to be compactified is what it's telling us is that it's a bunch of open arcs. And the heuristic is that the endpoints correspond to these broken trajectories. So we're achieving two things over here. We're first claiming that this moduli space of arcs can be compactified. Like it's a bunch of arcs and you can put some points in to compactify it. And you're also giving a geometric meaning to these points that you're adding. Okay. So all this under the fact of compactness. So the fact is that M check P minus P plus sits inside M check plus, which is compact. And in one specific case, we can even say more. If index of P plus is x P minus 2, then so generically, this turns out in the case when the expected dimension is +1, this turns out to be a compact one-dimensional manifold generically. So this is where I'm using things like, okay, first this is M check is a manifold of the right dimension and that it can be compactified to give a manifold again. So we don't have things like an arc that somehow, sort of loops in. Okay, so what does this bias? This, not only this, we can also say this, that in this case, so it's compact and we know what the boundary is. This is the boundary part is supposed to correspond to gluing and the compactness is, well, compactness. So now the point is that the oriented boundary of a compact one manifold is going to always sum to 0. So if you had a segment, then the two endpoints are oppositely oriented, and if you had a circle, you just have none. So what this buys us is that this count is 0, but this count from this gluing thing is just check. So This is great because now we have an intrinsic proof of d squared equals 0 within this formalism. And since all the earlier part of the formalism is supposed to go over to infinite dimensions, this now puts the proof of d squared equals 0 on this property of compactness and gluing. So in the infinite dimensional story, what we need to care about is, okay, we have these moduli spaces. Can we ensure they're compact? Can we ensure that in this specific case, when the expected dimension is +1, that it can be compactified to a one manifold boundary. So this is all that I have prepared for today. So I'll stop here.
Technically, the d squared equal to 0 boils down to saying that's a one manifold, a compact one manifold that's boundary 0.
Yes, with oriented boundary 0. Yeah.
Look, quick question. So
Yes.
that's the fact that these are of expected dimensions, that is where the genericity is.
Yes.
hiding.
No, not just that, even in showing this, showing that the boundary corresponds to this thing, that you need genericity over there as well.
But so one of the inclusions is where I guess gluing comes in, right? Because if you're given two broken things, you want
Yeah,
to
you want to put them together to get a trajectory that's nearby.
Basically.
Yeah. That is the gluing part. The compactness thing is just going to be that the only way you can fail compactness is when you go to one of these broken trajectories. And so, yeah, the gluing is supposed to be the converse to that.
The indices don't differ by 2, but the larger, then is there some kind of equality again? Or?
Yeah, so then the right framework would be to call it a manifold with corners. So you would have, I mean, this can be made for, you can formally define it as like a stratified manifold with like, different strata of high codimension. So in the when the dimension is 1, then there's only codimension 1 strata, which is dimension 0 pieces, and all the higher codimension strata are just empty. And so that's why you can call it a genuine one manifold. If not, you can call it a manifold with corners. But I guess one other thing that I want to point out is that this strategy requires your manifold to only be a topological one manifold. You don't need to have smoothness of C1 or anything of that sort. And for manifolds with boundary, I think it's a little more cumbersome to talk about it in the topological category. So
in the gluing the process,
Mhm.
you'll get an approximate trajectory, and then you'll have to use some kind of implicit function theorem to get an actual trajectory. Right?
yes. The point is you approximate close enough. So to say more, what you will do is, let me draw this with red now. Yeah, you know what? I'll just draw a different figure. It's already crowded enough. So say these are your critical points, and this is your broken trajectory. Then your approximate trajectory is going to be follow almost all the way, and then sort of cut it off over there, and then follow all the way back. And if the place where you sort of do this cutoff business, if that is close enough to this critical point, then it's close enough to an actual trajectory that you can appeal to implicit function theorem. So in fact, to say a little more, you need some sort of uniform bound on the linearization of these operators as you get closer and closer to the critical point.
I have a question.
I can't hear you clearly.
Can you hear me now?
Yes, sort of.
Okay. So you mentioned a parabolic PD. So in this case, there's just an ODE, right? So which is clearly elliptic. What is the setup in which you're talking about a parabolic PD?
I'm not sure I caught all of that. You were talking about parabolic PDs, but I couldn't tell what you were asking.
Oh, you mentioned a parabolic PD somewhere. I mean, what
Yeah.
is the setup in which you're talking about this? I mean, there's an ODE here, right? So it's elliptic.
Sorry, the voice is still breaking up a little bit. Could anybody?
So are you logged into Teams? No, Siddharth.
I logged out.
Can you log in? Because I'm not able to log in, and then maybe
Okay.
you can
Yeah.
post the question in the comments.
Yeah, could you just type the question in the comments?
Sure, yeah.
Keep the comments there.
You turn off all your mics, whoever is logged in. Some feedback from somewhere.
No, I think if you have your cell phone in your pocket, maybe
It's, I mean, it's in a different pocket, so
No,
it should not matter.
Unless he's logged into Teams on the cell phone, it won't matter.
If it helps, I'll turn this off.
Mics.
We can read the chat box question there probably.
Okay, I've never used Teams actually.
Yeah, let me do that. Yeah.
Yeah, me neither. I mean, I can't find the chat box exactly.
Oh, okay.
Yeah.
Yeah. I think we can hear you a bit better now. Can you
Okay,
repeat your
okay.
question?
Yeah, okay. So my question was, you mentioned a parabolic PD somewhere.
Yes.
What is the setup in which you're talking about a parabolic PD? Because everything is elliptic here, right? It's a ODE in this case.
What is the setup in which you're talking about a parabolic PDE?
Oh, okay. Yeah, that was supposed to be an offhand comment, so I can expand a little bit more, but this is not of too much relevance. But what I meant was that suppose, your manifold was like some space of functions. Then what you want is that you want some F, okay, F is conflicting notation, but you want gamma to be something like R cross, say it's a space of functions on a manifold M. Then you want M to say R, okay? And now say your function was, I don't know, some function which had linearization, the Laplacian. Then in this case, what you would have is you'd have gamma, so it would have something like del t gamma t comma x plus the Laplacian on x is equal to 0. Something of this sort is what you could have if the gradient of whatever thing you had on your space of functions was the Laplacian. Or in general, if it was some random elliptic thing, then it's del t plus some elliptic thing is equal to 0. And that was what I meant was parabolic.
I see. Okay. So I suppose the Instanton equations will be like this.
Yeah, they will be, but we'll do something more to there'll be some additional symmetries that we'll exploit to actually make it look better.
I see. Okay. And one more question, if you have sort of the time, which is, this is sort of, I don't know, but is there, do you know if one can formulate all of this instead of doing the analysis, one can explicitly write sort of the virtual, I mean, instead of writing down the moduli spaces, create some kind of virtual moduli spaces. I mean, create a Kuranishi chart for these very explicit Morse moduli spaces. Do you know if there's some reference where someone has written this down or something?
I think I lost you in the middle. So you wanted a reformulation of the moduli spaces for
in terms of Kuranishi charts for this explicit case, Morse theory.
Oh, for the explicit case of Morse theory, you wanted, some discussion about these moduli spaces and this framework?
Not in your framework, which is where you're doing analysis, but
okay.
Can you write down explicit Kuranishi charts for these, let's say?
I think I still didn't hear the last part. What was said? Explicit what?
Explicit
Banach spaces. Is that
Kuranishi charts, not Banach spaces.
But in any case, for a reference for a lot of this thing, I would say is Nicolescu's invitation to Morse theory. I think that should have that, and the references contained therein should have a more thorough discussion of this in the finite dimensional Morse theory context. So hopefully what you're looking for can be found there. Or if you can write in the chat, maybe I can look at what the actual phrase you were using.
Sorry, can you read?
Okay, yeah, I'll ask you later, sure.
Can can you just?
Can you ask him to repeat?
Can you hear me?
Yes, I can.
Okay, I think now it's better. So can you repeat the question?
Yes, my question was, do you know if one can write explicit Kuranishi charts for these cases?
Oh, you mean explicit coordinate charts?
Not
for-
coordinate charts, Kuranishi charts. Like, can you
Oh.
reformulate this in terms of virtual fundamental classes and so on?
Yeah, that's a little. It's tricky in the sense that you can. I'm on, right? Yeah. Okay. You can formulate local Kuranishi charts. Yeah. Sorry. Yeah. Let me repeat the question. So the question was, can you have some explicit Kuranishi charts for these moduli spaces? And the answer is, I don't really know. I mean, the question was also, having an eye towards defining some sort of virtual fundamental class or something of that sort. And at least in the Instanton scenario, I don't know a good answer to that question beyond saying that people care about local Kuranishi models. And in the Instanton case, this can be found in, I think there's a book called L2 Moduli Spaces by Roca, Ruberman, and Morgan, I think, which has some description about this. And yeah, I don't know of any other good place that has this other than, I guess, John Pardon's papers.
Perfect, thanks. Thanks a lot.
Any more questions?
Let's thank the speaker again. And we'll meet again.
So yeah, I don't know why there was feedback whenever I moved close to.
Yeah, it's because when you move there.
Yeah.
Feedback, right? Not.
Yeah, so I think this needs to be just
From the
centered.
speakers into this.
Yeah, I think
Yeah,
there's
it's
the feedback from the speaker to this.
speaker,
So
of course,
maybe you can just
yeah.
keep
Should
this.
we just
in
end the
center.
meeting though? Yeah.
Yeah, I started recording 5 minutes into the meeting.